On the 9th of May, 1985, a single event in Switzerland transformed how engineers think about stainless steel. In the small town of Uster, a lakeside community just outside Zurich, a quiet Sunday evening at the local swimming pool took a tragic turn. Around 40 swimmers were in the water when, without warning, the suspended concrete ceiling above them collapsed, crashing into the pool below. 12 people lost their lives, and many more were injured. The collapse stunned Switzerland. The pool had only been open for 13 years, and nothing about the building's design seemed unusual. Investigators would quickly identify the culprit. The stainless steel rods that held up the ceiling panels had been silently corroding away, setting off a sequence of events that would end in collapse. This was completely unexpected. Grade 304, the most commonly used stainless steel, was chosen for the rods precisely because of its excellent resistance to corrosion. The disaster forced engineers around the world to confront an uncomfortable truth. Even though we call them stainless, these materials are by no means immune to corrosion. To understand what happened at Uster, we need to dive into the world of stainless steels, what they're made of, how they behave, and the unexpected failure mechanisms that can lead to disaster. Stainless steel is fundamentally an alloy of iron and carbon. That's what makes it a steel. But it's the other elements in the mix that make stainless steels remarkable materials. The most important of these is chromium, a hard, silver-gray metal. In the atomic structure of stainless steel, the chromium atoms are substitutional. They take the place of some of the iron atoms. What makes chromium so useful in stainless steels is its strong attraction to oxygen. When exposed to air, chromium atoms migrate towards the surface, where they bond with nearby oxygen atoms to form chromium oxide, a stable, chemically inert compound built from 2 chromium atoms for every 3 oxygen atoms. This creates a thin, continuous film of chromium oxide all over the part. The chromium oxide layer is only around 10 atoms thick, but even so, it acts as a highly effective barrier, preventing oxygen and moisture from reaching the iron underneath, which can cause it to rust. And best of all, the layer is self-healing. If the surface gets scratched or damaged, the oxide layer will reform almost instantly. To be able to form an effective protective oxide film, steel needs to contain at least 10.5% chromium by weight. This is the threshold at which a steel is considered to be stainless, with some stainless steels containing as much as 30% chromium. But the alloying elements in stainless steels do more than just form a protective chromium oxide layer. They also influence the atomic structure of the material beneath it. And when you change the underlying crystal structure, loads of key properties change with it: strength, ductility, corrosion resistance, and even magnetism. Iron can adopt 2 main crystal structures. The first is a body-centered cubic form, called BCC, with 1 atom at each corner of the repeating unit cell, and 1 in the center. This structure is called ferrite. At 912 degrees Celsius, pure iron becomes more stable in a different atomic arrangement and undergoes a phase transformation. The atoms shift from a body-centered cubic structure to a face-centered structure, where they pack together more closely and efficiently. This FCC form of iron is called austenite. Austenite transforms back into ferrite at 1,394 degrees, before melting to a liquid at 1,538 degrees. Similar transformations occur in plain carbon steels. But stainless steels work differently, because the alloying elements, mainly chromium and nickel, dramatically affect the stability of the FCC and BCC structures. Chromium is a powerful stabilizer of the ferrite BCC structure. At the concentrations used in stainless steels, above 10.5%, BCC is stable over the full range of useful temperatures. This is called ferritic stainless steel. Secondary phases can form under certain conditions, but the dominant crystal structure is ferrite. Nickel has the opposite effect. It's a stabilizer of the austenite FCC structure. If you add enough of it, 8% or more, it suppresses the transformation from FCC to BCC as the steel cools to room temperature. The result is austenitic stainless steel, a material that retains the FCC structure at all temperatures. These are the two main types of stainless steels, with the main difference being the presence of nickel. The differences in crystal structure give ferritic and austenitic stainless steels very different properties. You can see this for yourself. Grab a magnet and start testing stainless steel objects around your house: the kitchen sink, cutlery, appliances. If the magnet sticks, you've got ferritic stainless steel. This is down to how the atoms are arranged. In BCC structures, the magnetic moments of the iron atoms can readily align with an applied magnetic field, so ferritic stainless steels are magnetic. This doesn't happen as easily in FCC structures, so austenite is essentially non-magnetic. It can become partially magnetic when heavily deformed though, because large strains can cause the face-centered cubic structure to transform to another structure type, called strain-induced martensite, which is magnetic. Because they don't contain nickel, ferritic stainless steels tend to be much less expensive, but they're harder to work with. Austenitic grades are far more ductile and easier to form into complex shapes. Ferritic stainless steels tend to have slightly higher yield strength in the as-supplied condition, but austenitics harden when deformed and can reach much higher strengths than ferritics after cold working. And when it comes to general corrosion resistance, austenitic grades tend to outperform lower chromium ferritic grades, although higher chromium grades can achieve comparable performance. Excellent formability and corrosion resistance are exactly why an austenitic stainless steel, grade 304, was chosen for the sealing suspension rods in the Uster pool. Grade 304 is by far the most common austenitic stainless steel. It contains around 18% chromium and 8% nickel, which is why it's sometimes referred to as 18-8 stainless. A close relative is grade 316. It has slightly more nickel and less chromium, but adds 2 to 3% molybdenum, which provides even better resistance to localized corrosion. On the ferritic side, the most common grade is 430, which contains 16 to 18% chromium and essentially no nickel. Austenitic stainless steels are the most widely used, accounting for roughly 70% of global production, with ferritic grades making up 25%. The remainder is split between martensitic and duplex stainless steels, more specialist materials that make up 4% and 1% of global production. Martensitic stainless steels have similar chromium levels to ferritic steels, but deliberately include much higher carbon. The higher carbon content means the steel is austenitic at higher temperatures, but this form isn't stable at room temperature, and as it cools, the austenite has to transform. If it cools slowly, it transforms into ferrite and other secondary phases, but if it's cooled very rapidly, which is the goal with these steels, it transforms into martensite instead, a very hard, distorted crystal structure. The result is a high-strength material, which is then tempered to reduce brittleness while retaining strength. Duplex stainless steels are different from the other categories because of their nickel content, which is somewhere between the austenitic and ferritic grades. This two-phase structure restricts the motion of dislocations through the lattice, giving duplex steels higher strength than either ferritic or austenitic steels. Duplex steels also have excellent corrosion resistance, comparable to, or even better than, the austenitic grades. We can compare the mechanical properties of different stainless steels by plotting yield strength, the stress at which the steel begins to deform permanently, against elongation, a measure of how much the material can stretch before it fractures. Austenitic stainless steels tend to have moderate yield strength and high elongation, although when cold worked, their yield strength rises significantly due to strain hardening, at the cost of reduced ductility. Ferritic stainless steels have yield strengths comparable to, or slightly higher than the annealed, unhardened form of the austenitic grades, but exhibit lower elongation, which is why they're less suitable for forming into complex shapes. Duplex steels have higher strength than the ferritic and austenitic grades, thanks to their two-phase structure. And martensitic stainless steels have high strength, but low elongation, because of the inherently brittle nature of martensite, even after tempering. There's another family of stainless steels we haven't mentioned yet, the precipitation hardened, or pH steels. These can be martensitic, partially martensitic, and partially austenitic, or fully austenitic, but what they have in common is the addition of elements like copper, aluminum, or niobium. When subjected to a heat treatment step called aging, where the steel is heated to a few hundred degrees and held there, these elements form very fine precipitates within the microstructure. These precipitates impede the motion of dislocations and give pH steels exceptionally high strength, often while still retaining more ductility than conventional martensitic grades. The most common of these is 17.4 pH. It includes 3 to 5% copper, allowing it to form a fine dispersion of copper-rich strengthening precipitates during aging. So what actually went wrong at the Uster pool? How could a material chosen specifically for its corrosion resistance, grade 304, deteriorate so badly? This wasn't ordinary corrosion, but a far more insidious process. The environment above the suspended ceiling was surprisingly aggressive. Warm, humid air from the pool rose up into the ceiling cavity, carrying with it the chlorinated compounds that form when disinfecting chemicals react with contaminants in the pool water. As the moisture in the air repeatedly condensed and evaporated on the stainless steel rods, these compounds decomposed, leaving behind chlorides that would become increasingly concentrated over time. Chlorides are small, highly mobile ions that are uniquely effective at attacking the chromium oxide film that normally protects stainless steel. This can lead to pitting corrosion, tiny, highly localized corrosion sites, where chloride ions have broken down the protective film, making the steel underneath vulnerable to attack. These pits didn't remove all that much material from the Uster pool suspension rods, but they did act as potential initiation sites for something far more dangerous: stress corrosion cracking. Stress corrosion cracking, or SCC, is the initiation and growth of microscopic cracks that only occurs when three factors converge: a susceptible material, a corrosive environment, and tensile stress. All three were present at the Uster pool. The suspension rods were under a sustained tensile stress, not just from the weight of the suspended ceiling, but also from residual stresses introduced during manufacturing. These tensile stresses would open up microscopic cracks in the material, preferentially within the corrosion pits, which acted as stress concentrators. Any resulting plastic deformation at the crack tip would momentarily rupture the protective chromium oxide film, which the chloride ions in the environment then prevented from reforming. Without the protective film, the chloride-rich, oxygen-containing environment could attack the exposed metal at the crack tip, steadily growing the cracks. Temperature played a key role too, with the elevated temperatures in the pool hall making chloride SCC much more likely. The rods were hidden from view behind the suspended ceiling and were never cleaned or inspected, so the chloride deposits remained in place, allowing the cracks to continue growing until failure. It was only after the collapse that investigators discovered the extent of the damage. Of the 207 rods, 108 fractured during the collapse, with 94 of those showing evidence of chloride-induced stress corrosion cracking. One of the major issues was the use of 304 stainless steel. Although it provides excellent general corrosion resistance, 304, like many austenitic stainless steels, is highly susceptible to stress corrosion cracking in chloride environments. This is partially down to its face-centered cubic structure. It contains planes where the atoms are more closely packed than in body-centered cubic structures. The closer packing allows dislocations to move along these planes with less resistance than in the BCC structure, because atoms only need to shift by a shorter distance to reach the next stable position. This means local plastic deformation can occur at lower stress levels, and it's why austenitic steels have higher ductility. But it also means that material at the tip of a developing crack can deform plastically more easily under sustained tensile stress. This continuously ruptures the chromium oxide film and also facilitates crack growth, making these materials especially vulnerable to stress corrosion cracking in chloride environments. A second problem with 304 was its resistance to pitting corrosion in chloride environments. Engineers quantify this using the pitting resistance equivalent number. It's calculated based on the amount of chromium, molybdenum, and nitrogen in the alloy. With no molybdenum and only limited nitrogen, 304 has a relatively low Pren compared to many other stainless steels, making it more prone to the pitting corrosion that can act as initiation sites for stress corrosion cracking. The Uster disaster fundamentally changed how engineers specify stainless steel for chloride-rich environments. Although chloride stress corrosion cracking in austenitic stainless steels wasn't completely unknown at the time, it was thought only to occur at significantly higher temperatures, in fully submerged conditions. Today, for structural applications in challenging environments, like swimming pools, marine structures, or chemical processing facilities, duplex stainless steels are the preferred choice. Their two-phase microstructure makes them remarkably resistant to stress corrosion cracking. The ferritic phase is far more resistant to chloride SCC than austenite, so the growth of any cracks that initiate in the austenite phase slows down dramatically when the cracks reach the ferrite regions. Duplex grades deliver this SCC resistance, while also providing much better strength and toughness than fully ferritic stainless steels, making them better suited to load-bearing structural applications. The Uster collapse wasn't an isolated case. Several other pool failures were reported throughout the 1990s and 2000s, many of them caused by stress corrosion cracking in austenitic stainless steels. Stainless steels are remarkable materials, but only when used in the right context, with a clear understanding of how they behave under real operating conditions. In engineering, assumptions are part of every design, whether they relate to material behavior, loading conditions, environmental exposure, or any of the other countless variables that influence real-world performance. The challenge is recognizing which ones truly matter, and knowing when they should be questioned. Sometimes that means prototyping and testing, but it can also start much earlier, during the design phase, by building models, running simulations, and seeking specialist input. With that in mind, I'd like to introduce you to this video's sponsor, Onshape. Onshape is a genuinely impressive cloud-based CAD platform. It has all the core functionality you'd expect from a good CAD tool, like parametric part modeling, assemblies, and drawings. But unlike traditional CAD systems, Onshape is fully cloud-native. It runs entirely in your web browser, which means no installations or licensed servers. Everything just works, and you've always got the latest version of the software. Because your models live in the cloud, you can access your projects from any device, anywhere. This is amazing for collaboration. It's easy to conduct design reviews and get input from specialists. All you need to do is share a link. And multiple people can even work on the same model at the same time. Version tracking is built in, with every change automatically recorded, so you can see exactly who changed what and when. And if needed, you can easily roll back or branch designs. All of this leads to better, more efficient engineering, with fewer errors and better traceability, all while making design decisions more transparent. The professional plan takes things to the next level for commercial use, adding simulation capabilities, PCB Studio, toolpath calculations, advanced workflow, and revision control tools, and unlimited private cloud storage that protects intellectual property. Onshape is genuinely a great tool that I use all the time, and I highly recommend you check it out. Head over to onshape.pro/efficientengineer to get started for free. And if you're interested in the advanced capabilities of Onshape Professional, you can use the link to get a 6-month free trial. And that's it for this look at stainless steels. Thanks for watching.